Okay, welcome back, everybody. This session is a review for Chapter 8. Chapter 8 is Searching and Sorting Algorithms. I'm gonna go ahead and type for us what are we going to go over for this session. Sorry, let me hide this. So Chapter 8, we need to go over search, algos, linear versus binary. Then we're gonna go over binary, sorting algorithms. And we're gonna talk about two main sorting algorithms. We have bubble sort and we have selection sort. So with that being said, let's go ahead and speak about linear versus binary search algorithm. So first, what is a search algorithm? A search algorithm is a method of locating a specific item in a larger collection of data. So in case you see this question in the exam, the definition of a search algorithm is a method or a way in order to locate a specific item, a targeted item, an item that we are looking for in a large collection of items or large collection of data. So here, this section will discuss two algorithms for searching contents of an array or a vector, any container or collection of data. So what is a linear search? Linear search is also known by sequential search, is a method or an algorithm, is an algorithm that uses a loop to sequentially step through an array. So it uses a loop to sequentially step through an array or a container or a vector, any container basically, starting from the first item all the way to the end of that container. So basically, if I have an array that has some items in it, for example, let's say I have ID numbers 5, ID number 1, ID number 3, 14, 6, 7, 9, 4, 2, 15, 20, 31, 24, 19, 17, etc. So I have this container, and then some function or some code is gonna call a function that says search. I need to find the position of a target, some item, specific item that we are looking for. Let's say I'm looking for item number 2. I need to know which position this item is on. Remember the positions? The positions are starting from 0, 1, 2, 3, 4, 5, etc. So the first item is at location 0, and the last item is at location size -1, whatever the size -1. So if I have 20 items, then the last position is 19, because 0 to 19 is 20. So linear search is basically starting from the beginning and then checking, hey, item at index number 0, are you what I'm looking for? Are you the 2? If you are not the 2, then I move to the second item. I keep moving forward item by item in order to find where the 2 is. Once I find where the 2 is, then I stop and report. I report back, okay, I found item number 2 at index, for example, 6, 7, 8. At index 8. So this is linear. Linear is starting using a loop, sequentially starting from the beginning, from the first item all the way to the last item. So what's good about this and what's bad about this? The advantage of linear search is its simplicity. In code, it's very simple. It's just a loop that iterates from 0 up to the size -1 index. And on its way, it keeps it checking if the current value is what I'm looking for. So it's very easy to understand and implement. Also, it doesn't require the data in the array to be in any specific fashion. They don't have to be sorted, ascending, descending, etc. They can be random, just like you see in front of you, just random set of items. So linear doesn't require any specific order or sequence. However, it's inefficient. Why it's inefficient? Because if the array contains, let's say, 10,000 elements, then the algorithm will have to look at all 10,000 elements in order to find the target that we are looking for. So the best case scenario in a linear search, the best case scenario is finding the item at this location, at the very first location. But the worst case scenario is having the item at the very end. This way, if the item I'm looking for is at the very end, I have to go over all the set, which can be very consuming. So if a value is stored in the last element, the algorithm actually have to go all the 10,000 items. This is the disadvantage of a linear search. With that being said, the advantage or the feature that the binary search brings to the table is that in order to find an element, I don't have to iterate all elements, but it requires some order before it executes the searching algorithm. So what is a binary search? A binary search is an algorithm that is better than linear search, and its only requirement is that the items in the set to be sorted. That's the only requirement. If the items are sorted in the array, then the binary search would be the best searching algorithm to be used, because it doesn't have to iterate all the items, even in the worst case. Remember, there is a best case scenario and there is a worst case scenario. Anytime you build an algorithm and you want to put it to the test, there is always a best case test and there's always a worst case test, basically, and there's the average case tests. Let's go ahead and put an array for ourselves, and as mentioned, it has to be sorted. So I'm gonna put some items here. For example, I'm gonna go with 0, 3, 5, 7, 9, 11, 13, 14, 15, 19, 21, 23, 26, 27, 30, 31, 34, 44, 51. So notice the items are sorted. Anytime you have a set where the items are sorted, you better use binary search. Binary comes from the term binary. Bi means 2. So this binary search comes under the umbrella of a way called divide and conquer. Divide and conquer means you have a big problem, then you divide it or break it down into smaller problem, then you solve each smaller problem separately in order to solve the entire problem in a better and a more efficient way, dividing and then conquering the problem. For example, let's say in this case, I am looking for the value number 30. I'm looking for 30. I need to know what is the position of item equal 30. So in this case, I'm going to say this starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I know for a fact that 30 is on index number 14. If I do actually execute a linear search, it will take me 14 steps. Let's call it steps. It would take me 14 steps in order to find the position of 30. I have to go here, then here, then here, then here, 14 iterations in order to find number 30. However, with the binary search, what happens is first we divide the array into two, right in the middle. So we slice it in the middle. I'm going to assume that 10 is the middle just by looking at it. So binary search comes and slice the array in the middle. The fact that it's sorted, I can compare only these two items. If what I'm looking for is greater, then for sure my item is in this part. If the item I'm looking for is less than this number, then it is for sure in this part. So by only doing one step, which is slicing and then comparing, I got rid of half the data set. So I am left out with the other half. That's only with one step. So that's how powerful it is. Then the next step for a binary search is to, again, repeat, slice in the middle, and then compare. Now it happened that 30 is right in the middle. So let me put a worst case. In this case, I'm gonna say I'm looking for 26. So I'm looking for 26 just to give a better demonstration. So again, I slice in the middle and then I check, is what the one I'm looking for greater or less than? The fact that it's greater, then I am done with this part. I don't need to look in this part. The fact that it's sorted, then for sure 26 is on the right part. Then I slice again. Is my 26, the one I'm looking for, greater or less than? The fact that it's less than 30, then I don't need to look in this part. So with only two steps, I'm done with, I got rid of 75% of the data set with only two steps. So now that I know that this is the block I'm looking for, I go ahead and again, slice in the middle. I'm gonna slice here. So now I know that 26 is here. So hey, 26 are you here or less than this item? The fact that it is here, I no longer need to do anything. So I report back 26 was found on this position. So I found the 26 if I used linear, it's on position 12. If I used linear, I would have needed 12 iterations. But with binary, I only needed 3 iterations. I started in the middle, then I moved to this section, and then I moved finally to this section, only 3 steps. And that's the power of a binary search. So that's what you need to know. You need to know the difference, and then you need to know the code. The code is found in the book. Then we move to sorting algorithms. Sorting algorithms, there are a lot of sorting algorithms there. Let me let me play a video for you. Before I play a video, let me give you some background. Sorting algorithms are very useful and very needed and very used. It's not just a theory, it's not just a concept. You're gonna see sorting algorithms a lot in the code. A lot of problems require you to sort. And sorting is not just ascending, it can be always, okay, it can also be descending. Sorting is not always numbers or digits for values. It's not always sorting by age or sorting by a grade. You can sort by any criteria. Now, of course, under the hood, the algorithm will have to find some digital value to the criteria in order to represent it in the computer. For example, if you want to sort by colors, colors under the hood are digital values. It's not a color, it's a digital value. Red, green, blue, RGB. R has a value, green has a value, and blue has a value. When you combine these values, you come with a color. That's under the hood, but the idea as a programmer, you don't always sort only on numbers from the user's perspective. For example, of course, you used Google before. So let me go ahead and go to Google, and I'm gonna search for anything really. Bicycle. I'm gonna hit enter. You're gonna see that I found about, so Google is showing off here. Google is saying, oh, look how powerful I am. I found almost 1 billion results in only 0.59 seconds. It's not just that. It's not just finding a lot of results in a short time, but also these results are sorted. I'm not gonna look at the ads, I'm gonna look at the actual results, which start from here. These results are also sorted. This result, the fact that I see this at the very beginning, before this, and then I can go all the way down. I should see the pages, like I can go to the next page. Maybe they no longer do it. Oh, so now I can scroll infinitely. So the point is, these results are sorted, and the sorting criteria is relevance. Here, the results are sorted not by the bicycle size, not by the bicycle price, not by the bicycle color, but the results are sorted by the criteria of relevance, which out of all those results, which result is the most relevant for the user's search. So they are sorted. Another example would be if you go to Amazon, for example, or eBay. Let's go to Amazon, and then let's look for bicycle helmet. So again, I hit enter, and then I start getting results. I get most relevant result first. However, I can change this criteria. So I can sort by feature. I can sort by price, low to high. I can sort high to low, average, new, date. So notice now I found 1,000 results. Notice when I click, boom, sorted. They resorted it for me. They resorted all those results for me based on a different criteria. I can resort again, and so on, so forth. So sorting algorithms are everywhere. Now, you might say, okay, since I have a lot of sorting algorithms and I have a lot of usage and I need sorting algorithm, which algorithm is the best? Well, there is no best algorithm. Every algorithm has its own case, so it depends on your problem, and then you pick the right or the most or the best fit, the best algorithm for your case. For example, if you have random numbers versus partially sorted, if you have this case uh, in your data set, in your array, you pick one algorithm over the other. If your array is random numbers, then you pick one algorithm. If your array is partially sorted, you should pick another algorithm, because some algorithms are stronger than others on partially sorted arrays, and other algorithms are better for randomly sorted arrays. Another example would be is if your data set is big versus small. Some algorithms are very quick for small data sets. Other algorithms are very quick for big data sets. So the algorithm that is very fast on a small data set, if you execute it on a big set, you're overwhelming the algorithm. You're exhausting the algorithm, so it becomes very slow. You can tell by looking at the algorithm visualization, you can tell that it starts very fast, and then once it starts reaching high number of items, it starts becoming slower and slower and slower, and then if let's say it's 1 million items, it becomes very, very, very slow because it has to look back to see where to insert, for example, the item that it's currently on within the list that is sorted. It has to iterate all the million items. We can see this by a video that I usually show. I used to like when I was a student. Let's see if this is the one. Reject. So what does this say? So this is showing me the different algorithms, but I want to change the data set. So this is not the one. Let's try another one. Let's see this one, this for sure. Okay, this one. For example, here they are showing you that this data set has random numbers, random order. This is partially sorted, so almost sorted. Notice the data set, it's almost sorted, but not completely sorted. This one is reversed, and this one has duplicates. Some algorithms are better on unique data set. Other algorithms are better on duplicate unique set. So notice here I have different algorithms: insertion, selection, bubble, shell, merge, heap, quick 3. There are many more algorithms. So notice now I can say I need problem size 50. So between 20 and 50 there is insignificance really. It should have been 20, 1,000, 100,000, 1 million. Then you can see significance. For now, let's execute, and you're gonna see that some algorithms finish faster on random than other algorithms. The same algorithm that finishes fast on random might finish last on reversed. An algorithm might finish faster, might get number 1 on nearly sorted, but can get number 5 on few unique. So let's execute. Now they are gonna start sorting. Which one is about to finish? Let me get rid. So I see, I'm looking at the first row. So heap finished. Heap finished. So it seems like heap finished first in all of them, which is very good. Because the data set is small, heap is slow on large data set. Some algorithms are still going. For example, insertion sort finished here, but didn't finish here yet. So you can, this is the link, you can view it. Another thing I need to show you is this video. Let's stop it. Let's open YouTube instead. Let me slower it down. I'm gonna go with 0.5. This video is very useful. It tells you here behind the title, if you see, it tells you the sorting name, then it tells you the number of comparisons so far, it tells you the number of accesses so far, and the delay between each iteration, just for you to catch up as a watcher. So the point here is what I need you to know is making comparisons is exhaustive. The more comparisons your algorithm makes, the slower it becomes. Also, accesses. The more memory access you do, the slower your algorithm uh, executes. So the lesser comparisons and the lesser accesses, the better. If you can find an algorithm or you can create an algorithm that sorts an array with the minimal comparisons and minimal array accesses, then your algorithm is the best. There is always minimum uh, that you need to do. For example, you can't sort an array in one go. You have to go multiple iterations. I can't, if you give me a random um, array, an array that has random order, I can't just sort in one go from left to right. Imagine you're playing cards and the dealer deals papers. You are playing 4 players in traditional deck of cards. There are 52 cards. So 4 players, every player gets 13 um, card. All 13 cards would be on front of you on the table, and then 3, 2, 1, you grab those 13 cards and you need to sort them. Can you sort them in one go? It's impossible. You have to go first card, okay, put it here. Then you need to repeat. Okay, go back. The second card. Where should I put the second card? Here. Then you go back. Third card. Here. Fourth card. Here. So there has to be multiple iterations. With that being said, let's watch, and you're gonna notice this can give you an idea how the selection sort works. Selection sort will basically go for on each iteration will keep track of the largest item, and once it reaches a specific, it reaches the end of the data, it will select. That's why it's called selection sort. It will select the largest item and puts it at the end. Then it will make a new iteration, and on the way it's iterating, it will keep track of the largest item so far. Once it reaches the end of the data set, it will select the largest item and puts it at the end. So let's watch. So I don't know if you see there is a green. Let's play more. So notice the green. So those are sorted so far. What's happening is the sorting algorithm is going from here all the way to the right. And on the way, it keeps a track, okay, which item should I pick next? It keeps a track of the item that should be picked next. For example, this one, or maybe this one. And once it reaches the end, it will select the one that it kept track of and puts it here. Then it will repeat. So multiple iterations. So I know it's annoying for the voice. I want to show you the normal. So the normal is kind of giving you a sound effect too. This one is insertion sort. So this is, for example, how I sort my playing cards. I look at all of them and then I start picking what I need and then insert it. Then picking what I need, insert it. So though these are sorted, then it picks the next one, or well, this is the next one. It picks the next one and then goes and insert it in the right spot. Then it continues. It picks the next one and goes and insert it in the right spot. That's why it's called insertion sort. So I'm gonna mute and lower the speed for you so you can see how it's doing it. Let's lower it more. So notice it picks the next one and goes and inserts it. Keeps doing this until the entire data set is sorted. Next one is quick sort. This is called quick sort, and it is under the umbrella of divide and conquer. Next one is merge sort. Merge sort is also under the umbrella of divide and conquer. It sorts smaller pieces and then merge them together. Sorts smaller pieces and then merge the two sorted pieces together. That's why it's called merge sort. Heap sort. Yeah, I'm trying to move forward because you can watch it on your own. I don't want to spend, I don't want you to spend a lot of time, but this is the idea. The book is asking you to know in code, and it has the code about two algorithms. One is called bubble sort. One is called selection sort. Selection sort, we saw it. It iterates and keeps track of the largest and then selects it and puts it at the right spot. Bubble sort is called bubble sort because it iterates and keeps a track of the largest item, not keeps track, moves the largest item while it's moving. That's why it's called bubble, because the largest item will bubble to the end. So basically, it will start. Let's say this is 8, this is 1, 3, 4, 6, 7, etc. So it will start here. It will pick this item, and then it will compare it with the 8. Hey, which one is bigger? If 8 is bigger, the fact that 8 is bigger, then 8 comes here and 1. So it swaps them. So 8 was moved. Then 8 will be moved again, moved again, moved again, moved again, etc. So the fact that 8, because 8 is the larger, in this example, it bubbles to the end. So if we do this multiple times, one iteration, second iteration for a different time. So I start at this item, then this item, this. For each item, I do an iteration and then I bubble up the largest. It's called bubble sort. I will end up with a sorted algorithm. So you need to know these two algorithms with their code, and the code is in the book. Go ahead and type it down and practice it or follow the book. You can ask me, you can send me questions, and that would be it for this chapter.